Hello everyone, welcome to the second class of Covid-19 AMC 10 prep. I am Anna, and let's begin today's lesson. Today's lesson is about geometry, and our focus is on circle and spheres. We're going to talk about cyclic quadrilateral today. Power of a point. And last, 3D geometry. So first, let's start with cyclic quadrilateral. And some of the fundamental properties. So first of all, the definition of a cyclic quadrilateral. So if I have a circle and there is a quadrilateral inside, which is ABCD. ABCD is defined as a cyclic quadrilateral. So a more clear definition is that a cyclic quadrilateral is cyclic if and only if the quadrilateral can be inscribed in a circle. So in this case, ABCD, quadrilateral ABCD is inscribed in a circle. That's its definition. And now some properties. The first one is that the opposite opposite angles add up to 180. And the second one, which I will show you a diagram, is that angle ABD, just this one, equals to angle ACD, which is this one. Angle BCA equals to angle BDA. Angle BAC equals to angle BDC. And angle CAD equals to angle CBD. So these are actually basic fundamental properties of a circle. So in a circle, if a two angle has the same arc, so this is the arc right here, these two angles are the same. The second thing I'm going to talk about is a theorem which states that AB plus CD equals to EF. And some of you might be wondering what are those letters, and I'll explain right now. So in a cyclic quadrilateral, if this side is A, this side is B, this side is C, this side is D, AC is the small e, and DB is the small f, we have this theorem which states that A times B plus C times D equals to E times F. So to summarize and to make memorizing this formula easier, the product of the diagonals equals to the sum of the products of the opposite side. And now let's try to prove this theorem. So since this is a proof, I'm just not going to draw the circles because, I'm not going to draw the circle because drawing the circle just makes the diagram very complicated and you can't really see what's going on. So here is a cyclic quadrilateral. It might not seem cyclic, but assume it is a cyclic quadrilateral. And I extend CD to a point P where angle BAC, which is this angle right here, equals to angle DAP, which is the angle right here. So, and last part, I'm going to connect D and B. So, since ABCD is a cyclic quadrilateral, angle ABC plus angle ADC should equals to 180, and this is the first fundamental property we talked about. Therefore, angle ADP should equals to angle ABC, because angle ADP also plus angle ADC equals to 180, so these two angles should be equal. And since angle BAC equals to angle DAP, which is these two pink angle that I labeled, we can say that because these two angles are the same, triangle ABC should be similar to triangle ADP. Therefore, AB over AD should equal to BC over DP. And this could be written as DP equals to AD times BC over AB. Then we try to prove another similarity. So because angle ABD, which is this angle right here, equals to angle ACD, this one, because they have the same arc AD, remember ABCD is the cyclic quadrilateral, and angle DAB equals to angle PAC, which is this one, these two. We can see that what we did was we make these two pink angles equal, and if both of them plus an angle DAC, it turns into angle PAC and angle DAB, and these two angles should also be equal. Therefore, we can say that triangle BAD should be similar to triangle CAP. So, AB over AC should equal to BD over CP, and this could be written as CP equals to AC times BD over AB. And we can see that CP actually equal to CD plus DP. And on the previous page, we actually write that DP equals to AD times BC over AB. So we can therefore write CD plus DP, which is AD times BC over AB, equals to CP, which is AC times BD over AB. And if we times AB on both sides, we can see that AC times BD equals to CD times AB plus AD times BC. And that is our theorem. So next, let us talk about power of a point. In power of a point, there are three scenarios. The first one is this one. We have two line segments and they intersect at point E in a circle. And power by point basically states that AE times EC equals to BE times ED. So AE times EC equals to BE times ED. The second scenario is this one, where point A, line AB is tangent to the circle, but BD intersect with the circle with point C. And then we will have AB squared equals to BC times BD. And this third scenario would just be this one, where point C is outside and AC intersect with the circle in point B and CE intersect with point D. And we will have CB times CA equals to CD times CE. We can see that these three scenarios are basically talking about the same thing. It's just whether this point right here is inside or outside the circle, and whether the line is tangent to the circle or not. Now, let's try to prove it. Since I said that these three are technically, on the fundamental level, the same thing, we're only going to prove the first scenario, which is this one. Here, I am going to connect AB, CD, and I connect BC mainly for demonstration purpose. So, because angle AEB equals to angle DEC, and this should be obvious because these two angles are opposite of each other, and angle CAB equals to angle BDC, and this is the reason why I connect this pink line, because they have the same arc, BC. Since we have these two angles equal, we can say that triangle AEB should be similar to triangle DEC. Therefore, AE over EB should equals to DE over EC. And if we cross multiply, AE times EC equals to DE times EB, which is exactly what we want to prove. Last, we're going to talk about 3D geometry. So, some people might be very confused about how to solve 3D geometry, and the general rule here of solving 3D geometry is to turn a 3D to a 2D. So we turn something that is really hard to solve, very hard to imagine, into a 2D, which is something we're more familiar with. This rule is similar to polynomials, that we want polynomial with high degree, so for example 3x to the power of 4, and we want to somehow change it into, for example, 3x, so we can solve the question easily. So let me give you some example here about how to convert a thing from 3D into a 2D and solve the math problem. So for example, a sphere, we can put more emphasis on the radius and the center. Example would be, for example, this is a sphere, and it's hard to draw a sphere in a 2D plane, but this is a sphere and this is its center. And here is another sphere. And we can see that if we do a 90-degree angle, we can see that this is the bigger radius, this is the small radius of the circle, and this will be the distance between the radius and the plane. So this is a very typical example of how to convert a sphere to a two-dimensional diagram. Another one is cube. We can pay attention to the diagonals, its center, and length. So for example, if this is a cube, we can pay more attention to these diagonals. So these ones, these ones, these ones, these ones, and these ones. It might be very ugly in this diagram. So last, I'm gonna give you guys a question to try out. So this question is from AMC 10, 2019 AMC 10A. Question 21. So hopefully you guys can solve this. That's it for today. Today is a very short lesson. And yeah, thank you very much.